Hello, everybody. Hey, this is going to be our lecture on gravity on number 2. And the main topic of today's lesson is Kepler's laws. And let me try to move this so we get better view of this. Okay, so Kepler's laws of planetary motion. Let me see if I can fix some of this. All right, that's a little bit straighter. Now, you guys, Kepler was this scientist and mathematician back in the time of Galileo and Copernicus and Tycho Brahe. Now, you guys may remember that Copernicus was the person who came up with the heliocentric view of the universe, which was essentially contrary to the church's teaching. You may also remember that Galileo kind of got in trouble with the church over expressing some of these views. But regardless, there was this gentleman named Tycho Brahe who was a Dutch nobleman who had money, and he had an island, and he was interested in what Copernicus had discovered. And he had set up a laboratory with basically this big measuring device like a sextant. And he, over the years, measured the location of stars, like over 700 of them, and planets. Now, remember back then, this was before the age of the telescope, and planets just looked like stars. And the reason that they knew that they were planets is because the actual name for planets in Greek is wanderers. So when you looked at it you looked at stars or planets compared to the distant stars, sometimes they went backwards through time, which was weird. It should have everything should have gone in circles. Okay. Now, there was a guy way back when, 2,000 years before this, a guy named Ptolemy, which was a Greek philosopher and scientist, that came up with this rather complicated mathematical system to explain those wandering planets, and they're called epicycles, and it's kind of fascinating. But basically, Copernicus said, "Hey, it's much simpler if we just think about these planets going around." Now, Tycho Brahe hired Kepler to be his assistant and had all this data, and then he died, and Kepler essentially inherited all this data, and he spent 16 years trying to analyze the stuff, and which is even very impressive because he did not have any computers, or I don't even think logarithms were invented back then. So regardless, it was a pretty major achievement. So anyways, Kepler came up with these 3 laws, okay, which we will see has to do with gravity. But he basically figured out that planets and objects orbiting the sun moved in ellipses. And a reminder, you guys, of what an ellipse is, okay, is we can draw an ellipse like so, okay? And an ellipse, you guys may remember from math, and they're often called the conic projections. So if we had this cone, right, and we were to kind of slice it parallel to the bottom there, we would end up with a perfect circle. And if we were to kind of cut it here, then we would end up with a parabola, okay? Circle, parabola. And if we went parallel here, and we can think of another cone up here and went through there, this would be a hyperbola. And then the one we're interested in is if we went from circle to circle, we're going to end up with an oval. Okay, so this oval thing is an ellipse. And you may remember when you studied ellipses in math, you had this distance right here, which was the semi-major axis, and you had this as the semi-minor axis. And the distance from the center, to one of the foci, gave you the relationship of a squared minus b squared is equal to c squared. A squared minus b squared is equal to c squared. Now, we could have these two foci, and if these two foci are really far apart, right, then we're going to get this really super elongated ellipse. And if these two foci go together and they coincide in one point, then you're going to end up with a circle. So in the same way that all squares are rectangles and not all rectangles are squares, all circles are ellipses, but not all ellipses are circles. Okay, so there's something called the eccentricity. Okay, we'll call it E. It's eccentricity. Okay, you guys might have heard eccentricity as if to describe someone's personality. Someone that's very eccentric is kind of all over the place, not essentially circular. They're going to be kind of way out there. But it has to do from an ellipse here, and this eccentricity is going to be the ratio of C to A, that ratio of C to A. So whenever we have any planets orbiting, let's say the sun, and that was where he did it. The sun, okay, and I'm going to get rid of these other things here. The sun is going to be at one of the foci. The sun is going to be at one of the foci. Okay, now in this range of eccentricities, it's going to be somewhere between 0 and 1. Okay, it's going to be like this. So if it is equal to 0, that would be a circle. And if it was equal to 1, that would be a line. Okay, so if we look at the Earth has an eccentricity of 0.017. So that means the foci of that are really pretty close together. And that means the Earth has a pretty circular orbit around the sun. Now, I'm sure you guys have all read or are aware of that. At some point in our orbit, we are closer and farther to the sun. Now, the difference between when we're closest and when we're farthest apart compared to the overall distance is real small. So it's essentially a circular orbit, although it has that eccentricity that's really sort of small. Other planets like Mercury is going to have an eccentricity of 0.21. And that 0.21 is the greatest in our solar system as far as planets go. If you take something like Halley's Comet, now you may remember Halley's Comet is something that has a period of 77 years, right? So it starts way out in the Kuiper Belt, and then it comes in kind of pretty close to the sun and then goes back out. It has an eccentricity of 0.97. So in a lot of ways, it comes in on a straight line, just swoops around and then kind of goes back out. So that's an example. A lot of comets have a eccentricity that is going to be greater than or real close to 1. And if you have an eccentricity that's greater 1, it kind of becomes a hyperbola. So there are actually comets that would come into our solar system, go around the sun and kind of get boomeranged, but they never come back, right? So they're essentially, their eccentricity becomes greater than 1, and they never come back. Okay, so if we take a look at this. What Kepler showed through his data was that planets moved around in elliptical orbits, which is really hard because back then the precision of the instruments was really small, so that how he determined that some of these planets with nearly circular orbits were actually elliptical was tricky. Okay, so that's kind of that standard stuff. So in Kepler's second law, a planet sweeps out. It sweeps out equal areas in equal time. Okay, so if this was the sun, okay, and we had something, well, we'll use the Earth, right? So if we have the Earth right here, and in this amount of time, okay, in a certain amount of time, we'll call that time 1, okay, it goes this distance, right? Now, if we connect that with the sun, then the area, this would be the area that's swept out in this amount of time. Now, if we were way out here, okay, and when we get the closest approach there, that is called the perihelion. The perihelion is the name for the place where you're closest to the sun, okay? If we had something orbit the Earth, the name of closest approach is actually a perigee, so different name. And then the farthest approach for the sun would be the aphelion, and then epigee would be it for any sort of thing. So anyways, we're going to have this area out here. So area 1 time 2, area 2. So basically what Kepler realized was that this area here, now remember this area T1 would equal to T2, okay? Now, well, how could you have something that goes from here to here, okay? That's a long distance in a certain amount of time, and when you're way out here, you're going a smaller distance. How is that possible? Well, it has to do with Newton's law of gravity, okay, which the force of gravity is equal to big G m1 m2 over r squared, right? So we can realize here, when you are closer, when that radius is small, that means this force is big. Okay, so when your distance is shorter, that means there's a greater force of gravity. So when you're here and you're being propelled, you're being accelerated by the force of gravity between you and the sun. So in this case, the Earth and the sun, it could be Mars or Venus or Jupiter. So when they get closer, they're going to go faster, and when they're farther away, they're going to go slower because of that radius. Now, this radius right here, that would be for a circle, right? We could put in a squared, which is the semi-major axis. And that semi-major axis, I'm not going to prove it here, but you can prove that right there also works out. So what we're going to do is we're just essentially going to use the mean radius, and we will get into that. So the reason for this, by the way, the reason that this is going to sweep out equal areas is because the angular momentum of the first is going to equal to the angular momentum of the second, which has to do, you may remember, it's going to be R cross P. R cross P. So without going through the math on that, and I think they do a pretty good job in the book of talking about that. So Kepler's second law is planets carve out equal areas in equal time. Okay, now on to Newton's third law. And this is really where I'm going to give you mathematical equations to use to give me mathematical answers. We could do it with this, but we really don't have time to give you many questions along those lines. All right, so Newton's third law was that the ratio of the periods of two objects orbiting the same thing, like Venus and Mars orbiting the sun, the ratio of their periods squared is equal to the ratio of their radii cubed. Radii cubed. Okay, so I'm going to go through a sort of a similar. I'm going to go through sort of a similar derivation that we talked about yesterday. So you guys may remember that yesterday we talked about how to calculate the mass of the Earth. How to calculate the mass of the Earth, and we're going to use kind of that same logic. We're going to use some of that same logic to determine Kepler's third law. Okay, so I'm going to switch over here. And remember, if we have the Earth going in a circle around the sun, and yesterday we talked about the moon going around the Earth in a circular orbit. Again, Earth's orbit and moon's orbit is pretty circular. Okay, that means the force that's causing it to go around is the force of gravity, which we just talked about. So this is going to be the mass of the sun, and we'll talk about the mass of the Earth divided by the radius squared. And if we have something go in a circle, we're going to have centripetal force. Centripetal force is going to be mv squared over r. And again, yesterday we talked about velocity being the distance over time, which would be 2 pi over t, okay? Sorry, 2 pi r. It would go a distance of the circumference divided by the period. Now, I'm writing v, technically that's speed, right? But at any one instant, it's going to have a tangential velocity. So that's why we can still call it velocity. Regardless, we can now say that v squared is equal to 4 pi squared r squared over t squared. So now we're going to take this and we're going to substitute it in there. Okay, since the mass of the Earth is the one that's orbiting, it's actually going to cancel each other out. So we're going to end up with g, mass of the sun divided by radius squared, is equal to 4 pi squared r squared over rt squared. Okay, now this r is going to cancel out with one of those. This one's going to go up here, and we're going to go from r squared to r cubed. And now we're going to get everything on this side except for r and t. So we're going to have g, mass of the sun, divided by 4 pi squared, and that is equal to r cubed over t squared. All right, so this is a constant, right? Our g is a constant. Remember that g is the universal gravitational constant, which is 6.67 times 10 to the negative 11. We're going to have the mass of the sun, which works out to be about 2 times 10 to the 30th. And then we divide it by 4 pi squared. This ends up giving us a value of about 2.97 times 10 to the 19th. Okay. Now, that's not necessarily that important because it is a constant, but if you take a look at the period and the radiuses of the planets in our solar system, they essentially are all right around that value, And they might differ slightly due to the fact that they're going to interact with other planets as they go around the sun. So we're going to get little permutations as we go around. Okay, now here's the thing, is we call this one and this one, okay, then we can say, well, if it's good for 1, it's good for 2. And now we're going to cross multiply, and now we can get r1 over r2 cubed is equal to t1 over t2 squared, which is what we have with Kepler's third law. All right, so how do we use this? So if we take any two planets, then we can talk about either the radius or the periods. So there is this riddle that you may have heard of, and we're going to answer this question through mathematics, at least partially. Where in the solar system would you rather, it is so bad, so hellacious, that you would rather spend a year there than a day there? Where would you rather be because it is so bad you'd rather spend a year in a place than a day in a place? And the answer is Venus, as we'll see. Now, if you look up the length of a day on Venus, it's 243 days. Okay. Now, it turns out that Venus, the planet Venus, is actually rotating really slowly, really slowly. So obviously our day is 24 hours, which is one Earth day. We compare our one Earth day to the Venus spinning on its axis, and it's 243 Earth days, right? So a fairly long time. So what we are going to do is we're going to calculate this T, and we're going to use the radius of Venus and the period of Venus, and we're going to compare that. We're going to compare that to Earth. We're going to compare that to Earth. Okay. So let's take a look at these numbers. Okay. And so we're going to have and radius of Venus cubed divided by the radius of the Earth cubed is equal to the period of Venus squared divided the period of the Earth squared. Now we're going to make this easy because we're going to compare this. We're going to compare this with the length of a year on Earth. Well, the length of a year on Earth is going to be 1. Okay? And if you look on the inside cover of your book, there's some information about planets, and it tells you the distance from the sun to Venus is going to be 1.08 times 10 to the 11th, times 10 to the 11th meters. Okay? And for the Earth, it's 1.496 times 10 to the 11th meters. Now we can see that this times 10 to the 11th is going to cancel each other out. So we can get rid of that. And this is going to get cubed, and this is going to get cubed. And we're going to multiply by 1 squared, which stays the same. If we take the square root of that, we can solve for the period of a Martian, from a Venetian year compared to a Earth year. So we're going to have 1.08 cubed divided by 1.496. And we're going to take the square root of that, and we're going to end up with 0.61. Okay, so 0.61. So basically, a Venetian year is 61% of an Earth year. So now we can multiply this by 365, and we're going to get 224 days. 224 days. And compare that to a Venetian day, which is 243. You would rather be on Venus because it's so bad for a year than a day. Okay. So now your question of the day is going to use the same, information. But what I'm asking you is at what altitude, would you put a satellite so that it is in geosynchronous orbit? What altitude would you put it at to have a geosynchronous orbit? Now, what is the period of a geosynchronous orbit? And the answer is 1 day. The answer is 1 day because weather satellites, for example, are geosynchronous orbit. So when you see a picture on the 6 o'clock news, or you're looking at it online, you're going to see all of the weather kind of go through. But it's essentially a static picture because that satellite that's taking the picture is moving and orbiting at the same rate that the Earth is turning, hence geosynchronous. It takes 1 day for it to go all the way around. Okay. Now, what would be that altitude? Now, in order to use Kepler's third law, we need two objects. We need two objects that are going to go around the same object, and in this case, the Earth. So the other object that we know about is going to be the moon. And the moon has a period of 27.3 days, and that information is in the question. So essentially, you're going to set up those same things, except this time you are looking for the radius. You're looking for the radius. And remember, once you have the radius, right, you're looking for this altitude, okay? And it is the altitude plus the radius of the Earth that gives you the R, from your answer. So if you want to get the altitude, you have to subtract the radius of the Earth. All right, so that's all we have for this one. We will see you guys next time. Take care.